Welcome to
Nay.
Do it.
Channel Everyone. Okay, so today we are diving into something called SpecTM, Spectral Targeted Masking for Trustworthy Foundation Models. JJ, that sounds very specific and very important. But my brain just heard physics-informed masking, and now I'm picturing a tiny superhero mask for light waves. Help me out.
Chuckles, that's not a bad place to start, Isabel. Think of it like this. Many of the big AI models for things like analyzing satellite images. They learn by playing a game of hide-and-seek with the data. They randomly cover up parts of the picture and try to guess what's missing. That's stochastic masking.
But here's the problem. When you're looking at, say, a satellite image of a lake, the data isn't random. Light reflects off water and algae in very specific physical ways. Different colors of light or spectral bands carry specific information. Random masking ignores that physics. It's like trying to learn a language by randomly covering words, instead of strategically covering verbs to force understanding of grammar.
So it's not a smart way to study. You're just guessing blindly. And if these models are used to predict things like toxic algae blooms that affect drinking water, you want them to be trustworthy, not just good guessers.
Exactly. So SpecTM is the smart study guide. Instead of random covering, it strategically targets specific bands of light to mask. It forces the model to reconstruct, for example, a key blue-green band by looking at all the surrounding red and infrared data. It has to learn the real, physical relationships between them.
This is the core of their self-supervised framework. They don't just do one task, they combine three. Reconstruct the targeted masked bands, infer biooptical indices from the context, and even predict what the image will look like 8 days in the future. The model has to build a joint understanding that is grounded in spectral physics and temporal changes.
Whoa, okay. So it's learning the why behind the patterns, not just the patterns. And you tested this on Lake Erie with NASA's PACE satellite data to predict microcystin. That's the toxin from algae blooms, right?
Correct, and the results are compelling. Their model achieved an R-squared of 0.695 for predicting current weak toxin levels. That's a 34% improvement over a standard ridge regression model. More impressively, for the 8-day-ahead prediction, it scored 0.62 R-squared. That's nearly double, a 99% improvement over a baseline method.
The ablation study is key. They proved the targeted masking itself contributed a direct boost of 0.037 R-squared over random masking. It's not just the multitask setup. The physics-informed design is actively making the model better. And in low-data scenarios, which is very common in scientific fields, SpecTM was dramatically more label efficient.
So it learns better with less hand-holding. That's huge. But beyond the numbers, what does this mean for trustworthiness? Is it more interpretable?
That's a great question, because the model is forced to learn these cross-spectral relationships. We can start to ask it how it knows something. Which bands was it paying attention to infer a certain index? The hope is this leads to more interpretable, less black box foundation models for critical Earth science.
It moves us from models that are just statistically good to models whose learning process is constrained by our domain knowledge, physics. That alignment between the AI's learning objective and the real-world system's rules, that is a fundamental step toward trustworthy AI for science.
Fantastic. So it's like giving the AI a textbook of physics to study from, instead of just a pile of flashcards. Thank you both for climbing that ladder with me from superhero masks to trustworthy satellite AI. Really fascinating.
Thank you, Isabel.
Thanks.
And thank you for watching. See you next time.